Assalamualaikum warahmatullahi wabarakatuh, and very good day to all of my students. So for today we are going to learn on how to solve for a case study under multistage gas absorption column. So this question is already embedded in the slides notes. It is desired to absorb 90% of the acetone in a gas containing 1% mole acetone in air in countercurrent stage tower. The total inlet gas flow to the tower is 30 kg/mol per hour, and total inlet pure water flow to be used to absorb the acetone is 90 kg/mol water per hour. The process is to operate isothermally at 300 K and a total pressure of 101.3 kPa. The equilibrium relation for the system is y is equals to 2.53x. Determine the number of theoretical stages required for this separation process. Okay, so after we read the question, we need to identify the unit operation for this case study, whether it is distillation process, whether it is gas absorption process, whether it is extraction unit, and so on. So the keyword for this question is the word absorb here. Okay, the word absorb is the word for gas absorption process, and the other name is the gas liquid. Okay, so gas liquid is refers to the gas absorption process where the gas is the air mixtures or the inlet gases or gas inlet, and the liquid is the liquid inlet where the solvent that are going to be used to absorb the harmful gas from the gas mixtures in the gas inlet stream. And if you see, we know that it is countercurrent mode of operation, which is the direction of the gas and liquid will flows countercurrently, or we say it is different direction. Next is we identify there is three components in the case study, which is the number one. Okay, number one is the acetone. Okay, the second one is the air, and the third one is the water. So the acetone here is the harmful gas that contained in the air mixtures. That's why the acetone will be the component A. Okay, and the air here, okay, the air here is pure air, which is the carrier of the acetone, meaning in the inlet gases, the air mixed with the acetone, and it will be the air mixtures, or sometimes we call it as air pollutant. The air will carry away together the acetone inside the column. It will be a gas pollutant. So the air normally being denoted as B, and the C is the solvent. So for this case study, the solvent that have been used is the water. So the water will be the component C. So for A, it says it is the desired component. And sometimes we call it as the solute. Okay, and for B, okay, for B is the carrier. Okay, normally it is pure air. Okay, and C is the solvent. Okay, if you read back the question, it says that the process want to absorb acetone from the gas mixtures. So in a gas mixture contain acetone in air. So acetone plus pure air, it will be gas mixtures. So in the gas mixture contain acetone. So the process want to absorb acetone from the air by using liquid solvent, which is the water. So water will be used to absorb the acetone, as stated here. So meaning water will absorb acetone from air. Okay, so this is the fundamental of the gas absorption. So after we know, okay, this is the gas absorption, and we already identify the components that exist in the gas absorption, next is to draw the diagram for the gas absorption. But before we want to draw the diagram of the gas absorption, we need to identify the type of the gas absorption, because we from the fundamental, there are three common types of the gas absorption. One of it is single stage gas absorption. The second one is the multi-stage gas absorption, and the final one is the pack absorption column. So as I mentioned before in the class, to identify the types of the gas absorption, we see the last sentence of the question. So the last sentence says, determine number of theoretical stages. So they ask you to identify the numbers of stages that contained inside the column. So meaning it must be multi-stage gas absorption column. So after we identified it is multi-stage gas absorption column, next is to draw the diagram of the gas absorption. So the gas absorption contain 4 main stream: the inlet stream, the outlet stream. This is gonna be the inlet stream. This is gonna be the outlet gas stream, and they also have inlet liquid and outlet liquid. Okay, so this 4 mainstream is used in the gas absorption process. So this is the fundamental of the gas absorption. So this gas absorption is multi-stage gas absorption. Okay, multi-stage gas absorption. Alright, so to avoid confusion, okay, I write down here the name of the stream. So this will be the gas inlet, and this will be the gas outlet. This will be the liquid inlet, and this will be the liquid outlet. Okay, so in the gas inlet, it contains of air mixtures. Okay, where in the air mixtures, it contains of pure air, or the acetone, plus the air or pure air. So the acetone is A and the air is B, right? Okay, so as these two combine, okay, it will be the air mixtures, or we say that it is air pollutant. And the liquid here, liquid inlet, we are going to use solvent, water solvent. The word solvent is used to help the process to absorb the acetone from air, where the solvent will get contact with the inlet gas that come into the column from bottom to top, and it will contact countercurrently in the middle of the trace or stage of the gas absorption. Okay, so the gas outlet, okay, in the gas outlet, it contains of acetone, okay, which is acetone, very small amount of acetone. As the absorption process happen, the acetone here will be decreasing to the top. In the gas inlet, the concentration of acetone here is very high, but upon absorption process, as the water being able to absorb acetone inside its stream, so the concentration of acetone will be decreasing upwards. So over here, there is acetone, but maybe the concentration or the mole fraction of the acetone at the gas outlet will be very, very low, because it is impossible for any system to absorb 100% of the solute. So in here it contains a small amount of acetone plus the pure air, which is component E. And over here, liquid outlet, as the process happen, what will be the outlet stream will be the water solvent, which is C plus with the high amount of acetone, because acetone is soluble in the water solvent. And we notice that acetone in the liquid outlet concentration is very high. At this first point in liquid inlet, there is no amount of acetone as we use pure liquid solvent. Okay, so this is the fundamental of the multistage gas absorption column. So after we identify the component that will exist in each and every stream, we need to write down the denotation of the stream as well as the mole fraction of the stream. So for denotation for the streams as well as the mole fraction in the gas absorption multistage, we know that for the gas inlet it denotes as Vn plus 1. We already discussed this in the previous session. So this is Vn plus 1. Okay, and this n plus 1 is the numbering of the stages. It's not counted in the calculation, so it is just the name of the streams. So in the Vn plus 1, in this under Vn plus 1, it contains of the mole fraction for in this stream. Okay, in this stream, where for V or vapor, the mole fraction will denote as Y. So since we have three components here, A, B, and C, we write down for the three components which is contained in this stream, whether it has value or not. That will be the number 2. Okay, so this will be YA n plus 1, and this A n plus 1 will be the subscript. Okay, and the next one is Y en plus 1, YCn plus 1. So we consider there are three components in the streams. Okay, so in Vn plus 1, it is the flow rate of the gas inlet. Normally it will be in terms of molar flow rate or the mass flow rate, so it depends on the question. So the question giving you the value in terms of molar flow rate, so this Vn plus 1 will be in terms of molar flow rate, and this Yan, Ybn, and Ycn, it depends on the question whether it has value or not. But if you notice that in here we already write down the component that contained in the gas inlet, they just contain of component A and component B. What does that mean? It means that for component C, the value will be definitely 0 because only two components exist in the gas inlet. So Ycn plus 1 over here will be equals to 0. We just have value for Yan plus 1 and Ybn plus 1. A and B. So how can we get these two values is from the questions. Okay, so after this we identify the value from the questions. Okay. Alright, so after we consider on the gas inlet, after this we will extract info from the question. So next we will look into the denotation for the other streams. So we look for gas outlet. So for the gas outlet, the denotation of a gas outlet for the main stream will be V1. Okay, we already discussed it also in a previous class. So this will be YA1, YB1 and YC1. Okay, so this will be the value, whether it has value or not, that will be number 2. Okay, so this is subscript. Okay, so if you look into uh, the the component that we already put in here, they only just have value for acetone and air, because C is the liquid, so liquid will be not exist in the gas stream, so that's why YC1 over here will equals to 0 also, because C is water is in terms of liquid phase, so this gas inlet and gas outlet is in terms of gas phase, so that's why YC1 is equals to 0. We just have value for YA1 and YB1. Okay, so let's move on to the denotation in the liquid inlet. So the liquid inlet will be denoted as L0, and in the liquid inlet it also contain of mole fraction, so this mole fraction will denote as X, so this is gonna be XA0, XB0 and XC0. Okay, so this will be subscript. Okay, and then you look here, it just contain of C, component C in the liquid inlet, because we use pure solvent, so component A and component B mole fraction will definitely be 0 and the component C will be 1. Okay, the fundamental of this is, according to the Dalton's law, the summation of the mole fraction for each and every stream must be equals to 1, meaning XA0 plus XB0 plus XC0 must be equals to 1. So if you have the value for A and B over here is 0, so the rest will be 1 in XC0. Same goes to this one, YA1 plus YB1 plus YC1 must be equals to 1. Okay, YAN plus 1, YBN plus 1, YCN plus 1 must be equals to 1. So it is also applicable for the liquid outlet. So the liquid outlet, it denotes as Ln. N is equals to the number of stages. So the mole fraction will be X. We have 3 components. So repeat again, XAN, XCN, and this one is XBN and XCN. Okay, and then this is subscript. Alright. Then you look here, it just contain of value for component C and component A. So meaning component B here will be 0. So we just have values for component A and component C. Okay, so then after you draw or after you write down the denotation of the streams as well as the mole fraction, then the time for us to collect the info from the question to be put inside the denotation. Okay. Alright, so we move to the first sentence. It is desired to absorb 90% of acetone in gas containing 1.0 mole percent of acetone in air in counter current stage tower. So counter current means different direction here, from bottom to top of the gas phase, from top to bottom for the liquid phase. This 90% is means it means that the process able to absorb 90% acetone. So we know that after absorption process happen, the acetone, which is 90%, will be collected at the liquid outlet, because the acetone from the gas inlet will be transferred into the water solvent, or liquid solvent. So and we says that 90% of acetone will be able to absorb 90% in the liquid outlet. So that is the meaning of the first sentence. So we write down here. Okay, we write down here. In this stream, in this stream, 90% acetone absorbed. 90% acetone absorbed. So if you know that in the liquid outlet there is 90% of acetone absorbed, so where is another 10% acetone? So another 10% acetone will be go at the gas outlet, where the 10% acetone is going to be the unabsorbed acetone, where the system are unable to absorb another 10% acetone, and that 10% acetone will go out, or exposed to the environment together with the pure air. Okay, so meaning in here, in this stream, it contains of 10% unabsorbed acetone. Okay, so altogether it will be 100%. 90% will be collected at the liquid outlet, where the acetone is being diffused or soluble with the water, and the 10% acetone will be go with or exit in the gas outlet together with the pure air. So this is 10% absorbed acetone. Okay. Alright, so in the first sentence, it stated it is desired to absorb 90%. So we already know this 90% is where it's located in the diagram. And in the same sentence, it stated 1% of acetone in air. So in the same, in the same sentence, it says that in the feed inlet, in the gas containing. So meaning in the gas inlet, it contains of 1% mole acetone in air. So this 1% acetone, so our acetone is A. So it means that in the gas inlet, it contains of 1% acetone. So as the acetone is component A, so that will be the mole fraction for YAN plus 1. So normally for the first sentence, it must be the value for or the composition for the inlet gas, because the system wants to know the first at the first point, okay, how many harmful gas that enters into the column. So it has been stated here, they want to absorb 90% of acetone, but that 90% acetone contain 1% of mole fraction of acetone. Okay, the concentration. Okay, this 90% is not the concentration of acetone, it is the amount of acetone, which is we can calculate the amount of acetone in terms of mole per hour, or mass per hour. Okay, molar flow rate or mass flow rate. But if you notice that, okay, after the number here 1.0, and the stated mole or weight percent, it means that it is mole fraction or mass fraction. So for this one, it is a mass fraction, mole fraction. So for the mole fraction, then only we can put inside the value here. So in a gas inlet, it is 1% A. So over here it will be 0.01. Okay, 0.01, because 1%. 1 divided with 100. So it is 0.01. Okay, so after we put the value for y(an plus 1) is equals to 0.01. So let's move on to the next sentence that gives you the information. The total inlet gas flow to the tower is 30 kg/mole per hour. So that is refers to the total inlet gas. So this one is refers to the gas inlet values. So this gas inlet, which is in terms of mass flow rate, which is kg/mole per hour. So this is refers to the Vn plus 1 because it refers to the inlet gas flow rate. So write down here 30 kg/mole per hour. And for the next sentence is total inlet water. Okay, total inlet pure water. So we know that the water is the solvent. So this 90 kg/mole water is refers to the liquid inlet flow rate, and it is denoted as L0, as we already put the denotation before. So the liquid inlet will be 90 kg/mole per hour. So that is how we extract the info from the question into your diagram. Okay, so to stress again, okay, it is very important for us to do the denotation first in order for us to extract the correct information into the correct denotation. And for multi-stage gas absorption, the denotation for gas inlet is Vn plus 1, the gas outlet is V1, the liquid inlet is L0, and the last one, liquid outlet, will be the Ln. Alright, so the other information that we can extract from this sentence of the total inlet water is the word pure. Yeah, the word pure here, okay, give a value in your data or in your diagram, which is the word pure means the solvent that going to be used for the system is 100% purity of a solvent, which means it is 1. Okay, 100% of C, so the rest will be 0. Okay, which is according to the Dalton's law, the summation of the mole fraction must be equals to 0 for each and every stream. And the system give you a condition. The condition of the system is this system is operated at temperature 300 Kelvin, and it gives you the pressure total, which is 101.3 kPa. And the last one, the question give you an info about the equilibrium relation, where we know that this equilibrium relation is used to develop the equilibrium line later on. So the equilibrium relation is y is equals to 2.53 x. So this is all of the information that we have extract from the question. Okay, so move on to the our main agenda is to get the number of stages for the gas absorption, multi-stage gas absorption. Before we do further calculation, okay, let me recall back. Okay, in order for you to get the number of stages, we need two important lines. Okay, two important lines that need to be developed in your graph later on. The first line is the operating line, and the second one is the equilibrium line. So this equilibrium line is used, okay, the relationship that the question gives you, which is y is equals to 2.53 x, and for this operating line, okay, this operating line, how can we develop the operating line is basically we need 2 points to be plotted in the graph later on. Yeah, the point 1 that we need to plot in the graph is the coordinate of x a naught as your x-axis and y a1 as your y-axis. So this is point number 1, and you will also need point number 2 be plot in your graph later on, which is according to this diagram, it is xan with yan plus 1. Yeah, the coordinate of xan, and the y-axis is yan plus 1. Okay, so this is the main thing that you need to have the values, or the important values that you need to calculate first before you do further calculation. Okay, or maybe this gonna be your steps to calculate or to solve for calculating number of stages for the system. Okay, so if you notice that to develop the operating line, we need xa0, ya1, xan, and yan plus 1. So from your diagram, you already get the value for xa0, right? Okay, you already get the value for xa0, which is 0. Here, we already have the values, which is 0. Ya1 is still unknown, means we need to calculate for ya1. Xan, we don't have the value, thus we need to calculate for xan, and yan plus 1, we already have the value, which is 0.01 from your diagram. So meaning, in order you to get the P1 and P2, we need to solve for ya1 and xan. So that will be the steps of calculation. Okay. Okay. So where is the location of these two important lines in your graph? Okay, let me show you the graph. Okay, so let's say you have y-axis and x-axis in your graph, and this will be ya and xa, ya and xa axis. And when we do the scale, okay, we cannot do the scale yet because we don't know the value for ya1 and xan yet. So after we calculate all of the values using the material balance or certain calculation, then we can develop the scales of the graph, because it's very important to get the value or information on the all of the values first in order for us to plot the point which is visible in the graph paper. So if you write down the scale first and then after that then you calculate the values, maybe your values when you want to plot in your graph, it is invisible there because of the scale is too wide or too low. Okay, or too low of scale. Okay, so just imagine that, or just assume that you already have the value of all of these four. So this P1 and P2, after this, okay, when you plot in your graph, it will be located like here. Okay, if you use pure water or pure solvent, the P1 will be located here, as we see over here is when pure water, so xa0 is 0, so we have value for ya1. So this is the location of P1. Okay, this is the location of your P1, which is xa0 is 0, so 0 value for x, and we have value for ya1. So P1 here is the value for xa0 and ya1. Okay, so when you have these two values, then you need to plot in the graph, then you will locate your point number 1. And after that, okay, the second point is xan and yan plus 1. So you need to calculate for xan, and the value for yan plus 1 is 1. So normally the plotting for P2 is will be located like here, be somewhere around here, and we know that this coordinate is refers to the point 2, okay, P2, where for P2 is the coordinate for XAN as x-axis and YAN plus 1 value as the y-axis. Okay, that's why we need to calculate for value of XAN. Okay, YAN plus 1, we already have the value from the question, which is 0.01. So meaning somewhere around here, it must be 0.01 value. Okay, here the scale will be 0.01 because we plot for P2 here. Okay, and over here is XA0, so it will be 0. YA1, we don't know the scale yet because we did not calculate yet, okay, the value. Okay, so for let's say, okay, this is your illustration of P1 and P2. So your operating line is when you join these 2 points, okay, to be a line, okay, using your ruler, and it is straight line. So join P1 to P2, so this will be your operating line, or we simply put SOL, operating line. So settle for one line in your graph. So the next line is equilibrium line. Okay, as the question gives you a relationship of linear relation, y is equals to 2.53x. So for example, after we calculate all of the information, then we know, okay, the scale of x-axis as well as y-axis. Okay, we can simply calculate for equilibrium line data, okay, where we just need to calculate only for 2 coordinate because it is a straight line. Okay, so straight line just need to calculate for 2 points or to plot for 2 points only. So let's say, okay, so let's say the scale for x-axis, okay, here is we put like 0.001. Okay, so this is, I just assume. Okay, after this we will see back whether it is a correct scale or not based on your values of your operating line. Okay, so let's say, okay, you have a value for 0.01 as x-axis and you have a relationship of equilibrium line over here. So how can we develop the equilibrium line? Okay, how to develop the equilibrium line? We need to get or calculate for 2 points, okay, or coordinate of the equilibrium line by using y is equals to 2.53x. So how? Okay, so how to calculate or how to develop the points? Okay, so you can write down let or when x is a mole fraction x-axis is equals to 0. Okay, so when you substitute into the y is equals to 2.5x, it will be y is equals to 2.53 multiply with 0 because when x is equals to 0, so your value for y is 0. Hence, the first coordinate for to develop the equilibrium line is 0, 0, which is located at origin. Okay, so that will be your first point for your equilibrium line. Right. The next point, okay, the next point is when you do the second point of the equilibrium line is when, okay, when x is equals to, you take whatever value you got in the x-axis. So over here I just put 0.01 as my first range of the x-axis. So you let x will be 0.001. So how to calculate y? When y is equals to 2.53, So you multiply with the x value, which is 0.001. Then you press your calculator. What's the answer? Okay. You try to calculate by using calculator. 2.53 multiply with 0.001. The answer is 0.00253. So what does that mean? It means that the second coordinate for the equilibrium line will be x is 0.001 and the y will be 0.00253. So this will be the second coordinate for the equilibrium line. So when we want to plot in the graph, it will be 0.01 as x-axis and 0.02 will be the y-axis. So maybe when you plot, it will be 0.01, 0.002. So maybe somewhere around here. Okay, and then when you get these 2 points, so how can we develop the equilibrium line? So you take your ruler and then you draw a line, okay, joint the first point to the second point of your equilibrium line and use the same gradient, okay, elongate the line longer than the operating line like this. Okay, so you got the line, you don't just stop until the second point of the equilibrium line. You use the same gradient, okay, don't move your ruler but elongate the line and make sure this equilibrium line is more longer compared to the operating line. So that will be your equilibrium line. Yeah, this is your equilibrium line. Okay, so after the equilibrium line as well as the operating line already plotted in the graph, so how can we draw the number of stages is when we put a dotted line or a line here starting P2. Okay, you take your ruler, okay, and you do a line straight line until it touch XA. So this will be the benchmark or where you want to stop your developing the number of stages, and the number of stages will start from P1. Okay, use your ruler. Okay, from P1 you drag the line straight and touch the equilibrium line and straight upwards and touch the operating line and repeat the same step. Okay, touch the operating line. Okay, so until, okay, when you do this, okay, when you develop upwards, the next step is not touch the operating line because the operating line already stopped at P2. So meaning these stages is not counted as your stages yet, okay, or your stages in the final steps. So the number of stages will be 1, 2, complete triangle 3. Okay, so how can we calculate for the stages is when this one is not complete stages, but how can we know? Okay, the precise stages is when you calculate for this from this point. Okay, what color I want to take to make it clear? Okay, the red one. So if I emphasize at this part, okay, so this is 3 stages. So when you calculate the value of the number of boxes starting from this point to this point. For let's say you get around 18 boxes, or let's say 18 boxes, and you need to calculate for the box which is starting from this point and stop at the this green arrow, because this is the benchmark or where we need to stop the number of stages. So for let's say you get 2 boxes here, okay, so you just divide 2 with 18. Yeah, divide 2 with 18. So you press your calculator. What's the answer? 2 divide with 18. So you get like 0.11. So over here you get 0.11. So the total number of stages will be 3 plus 0.11. So your exact number of stages will be 3.11 stage. That's it. Okay, so this is the idea on how can we develop the number of stages. But for this case study, we need to calculate the correct value for YA1 as well as the XAN, because this still being unknown. Okay, this value YA1 and XAN. So if you don't have these two values, then you will not get the correct P1 and P2 located in your graph. And if your P1 and P2 is incorrect, meaning that your number of stages will be incorrect too. So P1 and P2 is very important to be plotted in the graph later. So as you refer to the diagram, okay, we just have the value for we already have the value for XA0, which is 0. Okay, we have the value for XA0 and also YAN plus 1, and we still yet to have value for YA1 and XA1. So we need to calculate for YA1 and XAN. Alright, so we calculate for we calculate for YA1 first. Okay, we calculate for YA1 first. Okay, calculate for YA1. Alright, so in V1, in V1 it is the total flow rate. Okay, total flow rate of acetone and air, as you see over here, acetone and air. So in V1 V1 is actually the V1 total. Okay, V1 total, but in the book it just stated like V1, but V1 is actually the total flow rate of the acetone as well as the pure air. So if we split the flow rate that contained in V1 total, it is going to be VA1, which is the flow rate for acetone at stream number 1. Okay, so this is VA1 plus with the flow rate of component B, which is pure air, so it's going to be VB1. So this is the definition of V1 stream or V1 total stream, where in V1 it contains of two flow rate of gas, which is the flow rate of acetone plus with the flow rate of pure air. So if we put in terms of denotation, it will be VA1 plus VB1, because A is the acetone and B is the pure air. Okay, so after we know, okay, this is the equation for V1. So as to get YA1, it is actually fraction of acetone, which is we want to have the value for YA1, so we need to calculate for YA1 in terms of fraction. So it will be YA1 is equals to when it is fraction, so vapor for acetone stream, when we divide with the total flow rate, okay, so we'll get the value for Ya1. So it is in terms of fraction. Okay, so this is the solution or the steps. Okay, so Va1 over V1 total. So the definition of Va1 is the amount of acetone flow rates, okay, that be in the gas outlet. So before we know the amount of acetone in the gas outlet, first we need to know what is the value that acetone that will enter into the gas absorption first. Because if you still remember, we have an info from the question is stated only 10% of acetone will be flow in a gas outlet. So meaning this Va1, okay, will contain of only 10% from total amount of acetone from this process. So it is not 100% acetone that will be go at the gas outlet. It is just only 10% of from the total amount of acetone, okay, coming from this process. So meaning at first we need to calculate for amount of acetone which entering into the gas absorption. Amount of acetone entering into column. Okay, so this one will be denotes as VAN plus 1. Why I say VAN plus 1 is because in VN plus 1 it contain of acetone flow rate and pure air flow rate. Okay, so VN plus 1, okay, if you want to make it clearer, in Vn plus 1 it is actually the mixture of acetone and air. So if you put in terms of, if you split the equation, it will be VAN plus 1 plus with the V for air, it is component B, so it is VBN plus 1. Okay. So the VAN plus 1 is the definition of the flow rate of acetone in the gas inlet, and VBN plus 1 is the flow rate of pure air in the gas inlet. And before I move further, okay, I just want to highlight another one more important thing is about pure air flow rate. So we know that pure air flow rate, okay, it is denotes as V prime actually. Okay, pure air which is for component B, okay, it denotes as V prime. But we know that the pure air value, okay, or V prime, we also says it is inert gas. Okay, the other name is inert gas, and normally we denote as V1. And we know V prime. So V prime will be exist in the gas inlet as well as in the gas outlet. So V prime in the gas inlet is actually the VBN plus 1. Because it is the flow rate, this VBN plus 1 is the flow rate of pure air. So it is similar to the value for V prime. And in the gas outlet, it also contains of V prime, where we assume that there is no loss of pure air throughout the process. So in here, we have the value for VB1. Okay, this one. This one is the flow rate of pure air in the gas outlet, so it is denoted as VB1. So it is also similar value with the VB1. So this is the definition of inert gas or pure air flow rate. Okay, so the same value. So meaning, if you get the value for V prime or VBN plus 1 in this stream or in the gas inlet stream, automatically you will know the value for V prime, which is refers to the VB1 in the gas outlet, because VB1 is used to calculate for V1 total. V1 total is very important to get the YA1, which is our main agenda, to get YA1 to solve for P1. Okay, so that will be your steps. Okay, so refer back to this amount of acetone entering into the column, which is VAN plus 1. Okay, so at first we know from the question, we know that the amount of acetone or amount of total amount of gas inlet, it is Vn plus 1, it is 30 kg mole per hour. Okay, here it is 30 kg mole per hour, which is yang ni lah, this one. Okay, 30 kg mole per hour. So actually VAN plus 1 is the when we multiply the total flow rate, which is Vn plus 1 with its mole fraction or with the acetone mole fraction in this gas inlet stream, which is YAN plus 1. Okay, you will have the value of amount of acetone entering into a column. We just multiply with the mole fraction of the acetone from the total flow rate, because we know in a Vn plus 1 it contains of two components, which is acetone and air, but we just want to know the flow rate of acetone that enter into the column. Thus we just need to multiply the total flow rate with the mole fraction of acetone only. Alright, so this will be subscript. Okay, so once you develop this equation, it will be Vn plus 1 will be 30, and then multiply with YAN plus 1, it is 0.01. So using your calculator, you press your calculator. Okay, 30 multiply with 0.01, it will be 0.3. Okay, so the answer is 0.3 kg mole per hour acetone. Okay, so total amount of acetone entering into tower, okay, is 0.3. That is the entering amount of acetone. Alright, so as we know, the total amount of acetone is 0.3. How can we calculate for YA1? Okay, so YA1 is just 0.1 is unabsorbed acetone. So from this 0.3, this is 100% of acetone, but from 10% only, so that means that it is equals to the YA1. So YA1 is equals to 0.3, which is from total, you multiply with the 10% of unabsorbed acetone. So this will be the flow rate of or the mole fraction of the acetone that will come out through the process. Okay, or if you want to make it clearer, maybe we can calculate. We can say, okay, like this. Okay, so this is the amount of entering acetone, which is VAN plus 1. So to get the YA1, YA1 is the VA1 over V1 total. Okay, so we need to calculate for VA1. So how can we calculate for VA1? It is actually, okay, 10%, okay, that will be in the VA1, or we will flow in the VA1 stream, multiply with the total amount of acetone entering into the column, which is you already calculate before, 0.3 kg mole per hour acetone. Okay. So what will be the answer? It will be 0.1 multiplied with 0.3. So it will be 0.03, right? 0.1 multiplied with 0.3, 0.03. So the answer is 0.03 kg mole per hour. Okay, per hour. So this is VA1 value. So we already have the value for VA1 value. So our aim is to calculate for V1 total. So in order to calculate for V1 total, we need to also calculate for VB1. And we know that this VB1 is also same definition as VBN plus 1 or V prime. So as we know, when we want to calculate for V1, we need to have the value for V1 here multiplied with YB1. But if you see in your diagram, you not have enough information to calculate for VB1. So we can move to the gas inlet information, because we know VB1 is also same the value as VBN plus 1. And to get the VBN plus 1, it is VN plus 1 multiply with the YBN plus 1. Then we get the value for VBN plus 1. The total flow rate multiply with the fraction of the component B, which is pure air. Then we'll get the value for flow rate of the pure air, which is VBN plus 1. Thus, by using the information from the gas inlet, we can calculate for VBN plus 1. So you calculate for VBN plus 1 is equals to Vn plus 1 multiply with the mole fraction of component B, which is YBN plus 1, it is BBN plus 1 okay. So when you substitute the information, okay, Vn plus 1 as stated in the question, it is 30 kmol per hour, oh sorry, 30 kg mole per hour, kg mole per hour. So you multiply with the YBN plus 1, which is we know that the summation of YAN plus 1 plus YBN plus 1 plus YCN plus 1 is equals to 1. So you have the answer for YCN plus 1 and YEN plus 1. So YBN plus 1 will be 1 minus 0.01. So what will be your answer? 30 multiply with, okay, so 1 minus 0.01. So 0.99 multiply with the 30. So 29.7. So your answer is 29.7 kg mole per hour. Okay, so this is the flow rate of the pure air, which is Vn plus 1. So we know, as you know the value for VBN plus 1, automatically you will know the value for VB1 because the answer is same. So this is also the same answer with the V prime, or the same answer with the VB1 because the definition is similar. Okay, the inert gas or pure air. So pure air in a gas inlet will be the same value as the gas outlet. So by using this value 29.7 as your VB1, actually we already have the value for VB1. So you can calculate for V1 total. So your V1 total value, V1 total is equals to V1 total is equals to VA1 plus VB1. So your V1 total, VA1 value that you already calculate here is 0.03. Okay, So plus with VB1 value. So this is VB1. VB1 value is 29.7. Okay, so the answer will be 29.73. 29.73 kg mole. Kg mole per hour. Okay, so this is V1 total. Okay, done. So after you calculate for V1 total, so our aim is to get the value for YA1, because YA1 is very important to plot your P1. So by using the value that you already calculate before, you will have the value for VA1, you have the value for V1 total. So the last part is to get the YA1, yeah, because you already have all of the information. So YA1 is equals to VA1 divide with V1 total. So the answer is your VA1 value is 0.03. Okay, you divide with the V1 total that you calculate before, which is 29.73. So your answer for the mole fraction of acetone at the gas outlet will be 0.03 divide with 29.73. So your answer is around 0.001. Yeah, 0.001 as your YA1 value. Okay. So you already solved for the P1 coordinate. So your coordinate will be, your P1 coordinate will be XA0 is 0. So YA1 will be 0.001. So done for P1 coordinate. So let's move on to the P2 coordinates. Alright, so to get the value for XAN, actually it used the same fundamental as what we calculate for YA1, where for XAN here, how can we calculate for XAN is when you divide the value for LAN with the LN total. So in here, LN, okay, in a liquid outlet, in LN, the definition of LN, or I simply put as LN total, okay, in LN total, it contains of the flow rate of solvent plus with the acetone. So the acetone flow rate will be the A, okay, so it will be LAN, okay, plus with the solvent flow rate, it is LCN. Right, so again in LN stream or LN total stream, it contains of flow rate of solvent plus with acetone. So if we split in this LN stream, it contains of flow rate of acetone plus flow rate of solvent, okay, which is water. Okay, so how can we get the value of XAN is basically we need to calculate for LAN and LN total, okay, where XAN is equals to, because it is component A, so meaning we need to use LAN divide with the LN total. If you want to calculate for XCN, so this will be replaced with LCN, but still you need to divide with the total. Yeah, it is the simple fundamental. How can we get the fraction from a mixtures? So whatever component that you want to calculate, no matter it is component A or component B or component C, so when you divide with the total flow rate, then you will get the fraction, its fraction. So in here, we want to calculate for XAN because XAN is going to be used to plot in the graph later on. So we just need to calculate for XAN. Alright. So to get the XAN, we need to have the value for LAN and LCN first. Okay. So the flow rate of the pure air, flow rate of the pure water or the solvent is denoted as L naught. Okay. So we assume that there is no loss of solvent throughout the process. Meaning your solvent is not easily vaporized, your solvent is chemically stable, is inert. Okay, so meaning whatever water solvent flow rate that you flow into your column will in the liquid inlet will be similar or same value as in the liquid outlet. It means that your liquid solvent, which is L naught in the first stream or in the liquid inlet, which is 90 kilomole per hour, kgmole per hour, okay, 90 kgmole per hour is actually the same value as L prime. L prime is the L inert and also same value as L A naught. Okay, where is your L A naught? L A naught is when L naught multiply with the X A naught. Okay. L naught multiply with the XC naught. Okay, and same value with the LCN, which is the liquid solvent flow rate that flows in the liquid outlet. LC naught is the flow rate of the solvent that flows in the liquid inlet. So in L naught, since it is pure water solvent, so it's just contain amount of solvent only, 100% of solvent. So L naught multiply with XC naught, you will get the value for LC naught. Okay, so this is LCN. So what I want to give you information here is since it is inert water solvent, okay, and we assume that there is no loss of solvent, so the value for L naught is similar with the LC naught as well as the LCN. So by right, we already have the value for LCN, which is the value, the amount is still 90, okay, which is 90 kgmole per hour. So next job is to calculate for LAN. So the definition of LAN is the flow rate of acetone, okay, in the liquid outlet. How can I know it is in the liquid outlet? It's because of the N stream. So this is LN. So LAN meaning in the liquid outlet stream, the amount of acetone that flow out in the liquid outlet stream. So LAN, okay, I want to calculate for this one in order for me to get the value for LNT. So we need to calculate for LAN. So LAN is the amount of acetone. Why acetone? Is because the word A. Okay, this is A. A is for acetone. Amount of acetone leaving from leaving in liquid outlet. Okay, so based from the question previously, it stated that 90% acetone is absorbed here. This is absorbed, absorbed here. So meaning acetone, okay, in the LAN, there is only 90% acetone that will come out in the outlet stream. So meaning in LAN is just 90%. If you still remember, we already calculate the amount of acetone entering into the column, which is total amount of acetone, which is 0.3 previously. So from 0.3, 90% out of 0.3 will be amount of acetone leaving in the outlet as stated here, as the question gives you the information. Okay, so it means that here, okay, 90% or 0.9, okay, 90% or 0.9, when you multiply with the total amount of acetone entering into the column, which is you already calculate before, which is 0.3, you will get the value of amount of acetone leaving in the outlet only for acetone, because we consider for LAN. Okay, and also the information give you the information for acetone only 90%. So 0.9 multiply with 0.3, we will get 0.27. 0.27, don't forget the unit, kmol per hour. So this is acetone leaving in the outlet. Okay. Okay, acetone leaving in the outlet, which is your LAN. Okay, your LAN. So then, how after you get the value for LAN, meaning you can solve for LN total, right? So we already have the value of LCN, which is 90, because it is similar value with the L naught, L prime. Okay, and you get the value for LAN based from this information that question gives you from the total amount of acetone entering. You will get the 90% acetone that come out in the liquid outlet, which is 0.27. So press your calculator, calculate for LN total. LN total is equals to LAN is 0.27 plus with the LCN is 90. Okay, so it's going to be 90.27 kg mole per hour. Okay, so this is for LN total value. But we still not finished yet, because we want the value of XAN. So to get the value for XAN, as you see in this equation, it is LAN divided with the LN total. So the value for LAN that you already calculate here, which is 0.27, you just divide with the value of LN total, which is 90.27. Then you will get the value of XAN, 0.27 divide with 90.27, 0.02, okay, 0.27 divide with 90.27, so you get 0.002. So your value for XAN is 0.02. Then that's it. You already get the value for XAN, which is the coordinate for P2 here will be P2 is the coordinate will be XAN is 0.002 as your x-axis. YAN plus 1 is YAN plus 1 is 0.01, right? From the question. So we see again YAN plus 1, yeah, 0.01, which is based from the question. So done, you get P1, P2. So plot these two point inside your graph, okay, then it will be located P1 and P2 here. So XA naught here will be 0 with 0. Our YA1 is 0.001 that we have calculated before. So meaning in here, okay, your coordinate is correct. It is correct range. So it will be 0.01 that you need to do the scale. So this will be 0.001 scale. Then repeat with the same range. 0.001, 0.002, 0.003. When you want to stop, you look into the P2 coordinate. So P2 coordinate is XAN is 0.002 based from the calculation, and YAN plus 1 is 0.01 which is from the question. So 0.002 is actually somewhere around here. Yeah. So this P2, the actual P2, then when you develop your graph in your graph paper, it will be lay on at P2, which is here. This is your P2. So this is just the estimation previously, but the correct P2 is 0.002 with the P1. Okay, with the P1 is 0.01. So let's say when you develop the scale, so this is 0.01 and this is the location of your XAN, which is 0.002. So let's say this is your 0.002. Okay, and the intersection of the 0.002 with 0.01 is actually here. Okay, so your actual operating line according to the case study is when you join this P1 to the P2. So this is your P1 and this is the P2. So the previous one, the blue one, I just estimate the P1 and P2 coordinate, but after we calculate the actual value or coordinate of PA2, so this is the point located. Okay, so this is your P2 coordinate and this is your P1. So but the thing is, how can we get the number of stages is still the same as I mentioned before, where you need to develop your equilibrium line. Okay, right. So for let's say, okay, I erase the previous solution by using incorrect operating line or assumption of the operating line. Okay, assumption of the operating line. So this will be your operating line, right? So next is to develop the equilibrium line. So this one I also assumed previously. So let us see the correct equilibrium line that we need to develop, right? So as I mentioned before, when you want to calculate for equilibrium line, we need to get 2 points, as I explained earlier, where y2 coordinates is because the equilibrium line is straight line, as the question gives you a relationship of linear relation, y is equals to 2.5x. So of course the first point will be at origin when x is 0. When you substitute into the equation, the y will be 0 also. So this is your first point, and we what I can say, this is the correct equilibrium line because the range of the x-axis is similar that I assume at first step, okay, which is 0.01. So when x is 0.001, when you multiply with 2.53, so 0.002 will be your y-axis coordinate. Okay, but if you want to plot accurately, okay, so I erase this first. Okay, so according to the data that we calculate for coordinate of equilibrium line, okay, so you see this is your first point of equilibrium line. The second point is x is 0.001, which is this one, 0.002. So where is your 0.002? So at this point. So this is your equilibrium line point. So you take your ruler, okay, you take your ruler, you join these two point, okay, and using the same gradient, you elongate the line longer than the operating line. Yeah, the equilibrium line is much longer than operating line. This is the equilibrium line, and this is the operating line. And by using the same steps as before, you take a ruler from P2, okay, you draw a dotted line, which this will be your benchmark on when we'll stop the number of stages. And next step is to calculate number of stages starting from P1 using your ruler. Okay, I enlarge this diagram. So to get the number of stages starting from the P1, go to the equilibrium line straight line and go upward, touch the operating line will be your stage number 1. And repeat the same step, go to the equilibrium line and touch the operating line will be the second step, the third one, the fourth one, okay, and finish until the last steps. Okay, and how can we calculate for the last step is as I explained before. Okay, so here when you get your second, third, and the fourth stage, okay, so the last one you need to calculate the ratio to get the actual number of stages. Okay, here I want to do a little correction, which is when we calculate for XAN. Okay, when you calculate it, okay, you put 0.27 over 90.27. This is actually 0.03. Okay, 0.0029. So this will be 0.003. Okay, so a little amendment here. This will be 0.03. Yeah. Okay, so when it is 0.003, okay, so your point 2 will be 0.0034x. This will be 0.003. Okay, 0.003. So in your graph letter, point number 2, so this will be 0.003 also. Okay, so this will be 0.003. Okay, 0.003. So let's say this is your 0.003. So you please plot carefully in a graph. Okay, so according to the scale before, so here 0.001, 0.002. Okay, so again, if you I want to stress more on this scale. If you put 0.0 to 0.001 as 10 boxes, so make sure at x-axis also still the same. from origin to 0.001, 10 small boxes, 10 small boxes to 0.002, 10 small boxes to 0.003, and so on. Alright. Okay, so if you recall back to the slides, okay, you can see all of the information you already discussed or we already calculate before. Okay, starting from the mole fraction, the amount of entering acetone, the value for YA1, XAN to be used to plot the P1 and P2, and lastly we already calculate or we already develop our graph, which is including the equilibrium line and operating line. So when you do properly in your graph paper, the number of stages that you will gain is actually 5.2 stages. Okay, so you can try this at home. Okay, try to do the solution that according to my discussion before, okay, until you get the number of stages, which is 5.2. Okay, so by using the same case study, try to do also by using analytical equation to calculate the number of stages, where we need to use for this equation, where you get the value for A1, AN, A and N. So A1 is the absorption factor. So L naught here is actually your 90 kg/mol per hour, which is the inlet flow rate of water. So this M is actually the gradient of the equilibrium line, where the question gives you 2.53 if I'm not mistaken. So you can check back, okay, 2.53. So V1 here is the V1 total. So we already have the value for V1 total as you calculate before. Okay, so substitute V1 total here, then you will get one value over here. And then next to calculate for AN. So this Ln is actually Ln total. So Ln total, if you recall back that what we have discussed before, in Ln total is the summation of LAN plus LCN. So you use LAN value. This M is the equilibrium gradient for equilibrium line, which is 2.53, which has been given in the question. Vn plus 1 is the Vn plus 1 total. The question already gives you the value, which is 30 kg/mol per hour. So substitute all of the information and you will get the value for An. So next is multiply this 2A and then square root it, and you will get value of A. So this value of A you substitute into the final equation. Okay, this A, and then this Yn plus 1 is Yan plus 1. This X naught is Xa naught. This Xa naught is also Xa naught. This 2m is the 2.53, which is the equilibrium gradient. And this Y1 is the Ya1. So you take all of these values from your diagram, substitute into this equation, then finally you will get the value for n, which is the number of stages. And by right, you will get almost similar answer with the graphical method, which is 5.2 theoretical stages. So hopefully this kind of discussion or explanation will help you to understand well on this case study for multi-stage gas absorption column. Thank you.